and the session will be on artificial intelligence, machine learning, for additive manufacturing. So now I welcome our resource person, Dr. Piyush Shakya sir, for the session. So before going to start the session, I would like to now brief the profile of, I would like to briefly explain the profile of Dr. Piyush Shakya sir. Dr. Piyush Shakya received his PhD from Department of Mechanical Engineering, IIT Delhi in 2015. He finished dual degree BTech Mechanical Engineering and MTech in Product Design from IIT Madras in 2006. His research interests include structural health monitoring, fault diagnosis and prognosis, machine elements, rolling machine based GPS, and signal processing. He is interested in developing solutions capable of accounting for different types of variations present in manufacturing scenarios, data set to data set, variations, defect topography variations, etc. His professional experience includes from 2015 to 2016 research fellow in vibration diagnostics and prognosis, digital signal processing, Center for Cyber Physical Systems, School of Aerospace, Transport and Manufacturing, Cranfield University, UK. His research work included was diagnosis, root cause analysis of wares, and experimental investigations. Also, from 2006 to 2010, member research and development, crankshaft and piston group, engine section TVS Motor Company, Hosur, Tamil Nadu. His responsibilities were development and testing of crankshaft components for all platforms of vehicles, such as motorcycles, scooters, three-wheelers. And he also received many awards and honors, which includes Institute Silver Medal Award awarded by IIT Madras for securing the highest CGPA in the 7th and 8th semesters of dual degree in mechanical engineering and product design during the academic year 2004 to 5. GE Foundation Scholarship Award by GE Bangalore in the year 2004 to 6 for academic and leadership excellence during dual degree. Currently, Dr. Piyush Shakya is working as associate professor in the Department of Mechanical Engineering in IIT Madras. So, welcome you, sir, for the session. I request Piyush Shakya, sir, to take over the session forward. Sir, your voice is
Thank you
not
for the
audible.
kind introduction. I will share my screen now, and I will close this camera and restart the screen. Can you see this screen over here?
Yes, sir.
Okay, so I will start this. Let me make it full screen and then I will start. So the topic which I am going to discuss today, that is artificial intelligence and machine learning for bearing health monitoring. And this was my brief biodata, which anyway has been covered by the organizers. So I will skip the slide and I will come over here. So so the idea over here is artificial intelligence and machine learning is a entire subject in itself. And now we are going to discuss over here its application in bearing condition monitoring or bearing health monitoring. So bearing health monitoring in itself is a subject, and artificial intelligence and machine learning in itself is a subject. Uh, and what we are discussing over here is the intersection of these two. So what is artificial intelligence over here? So artificial intelligence is basically like, for example, there are a couple of things which humans can do very easily. For example, suppose if there is on floor there are so many red color flowers and there is one or there are few yellow color flowers, then like for a human it is very easy to identify or very easy to segregate or very easy to like pick yellow color flowers and put them separately. Same way, if on the floor there are all rectangles but there are some triangles, Even a child can pick all the triangles and put them separately. So that is what is basically segregation or classification, and even prediction and even prediction and forecasting is also easy for humans. Now these kind of things are basically taken up by artificial intelligence, that is basically computer system are trying to mimic these human cognitive functions which come naturally to humans, and that is what is basically artificial intelligence. It is basically having, it has multiple it has multiple subsets. One of them is machine learning. I will show a detailed slide where I will discuss what are all the areas which come inside artificial intelligence. So in machine learning, basically this is basically all about algorithms which make it happen, and it can happen in both ways. That is, it may need some intervention from humans, or it may not need any interventions from the humans. It may so happen that the entire, like we are simply giving the data to machine, and the machine itself by kind of puts different kind of labels to it, and it says that okay, this data should have kind of, like for example, when we are seeing that flowers example, nobody is saying us to nobody is mentioning us anything. We ourselves decide that okay, there are some flowers which are yellow, there are some flowers which are red. So we are ourselves kind of making those classes. That is basically is unsupervised machine learning. And if I tell there are some yellow flowers, there are some red flowers, and the classes are given along with it, that is called supervised learning. And deep learning is further a subset of ML, that is basically kind of more like neural networks, and it basically try to replicate the human mind, that is neurons and layers of it. But it should be brought over here that when we talk about human minds, there are crores of neurons that we are talking about. It's not one neuron or two neuron or three neuron or something like that. While in deep learning, whatever you do, your number of neurons, the number of layers remains limited. So since the number of neurons remains limited, and therefore what happens, that whatever is the accuracy of deep learning, that is never same as whatever we are getting as per human mind. So this is what is a slide to get that idea, that when you see over here, you can see that artificial intelligence is the entire thing, and then machine learning is a subset of it, and deep learning is further subset of it. Now if you see it differently, then you can put it like this. So the top you are seeing, that is artificial intelligence. Within artificial intelligence, you may have machine learning, natural language processing. See, nowadays we have so many things, no? Like for example, nowadays there are apps that basically there are so many Indian languages. So for example, if I speak in some Indian languages, let's say I speak in Kannada, and it will translate, and it will say everything in Telugu, or it will say everything in Tamil. That kind of softwares are already available. That is what is natural language processing. That is, we are taking one language, and we are kind of changing into another language, and that is very useful for a multilingual country like India. And same way over here, there are some expert systems which are basically for a particular kind of task. Now same way, speech and vision, they're also there. For example, you can write some text, and it can be spoken, or you can click a picture, and that is kind of vision, and it will search all those things, Google Lens and all. So all that is basically artificial intelligence. Now same way, planning and robotics. Now when you talk about only machine learning, you can kind of divide into three parts, that is supervised, unsupervised, and reinforcement learning. And within that supervised and unsupervised, you can take it as deep learning, that has convolutional neural network, that is CNN, recurrent neural network, that is RNN, self-organizing maps, that is SOM, autoencoder, and other things. So what is that machine learning? That the one slide you are seeing over here. So in supervised learning, what happens, that you give the data and you provide the labels. So for example, you tell that the data which I am giving to this machine, it has three different classes. Like in case of bearings, it could be like, in case of bearings, it could be healthy bearing, and mild defect bearing, medium defect bearing, or severe defect bearing. These kind of classes you are providing directly. However, like for example, in case of flowers, it could be red color flowers, yellow color flowers, or some other color flowers. That is different classes you are defining by itself. So if that kind of thing is happening, then whatever techniques are used in that, that is called supervised techniques. And examples of that are basically SVM, that is support vector machine, discriminant analysis, naive Bayes, nearest neighbor techniques, random forest and all. And the second type is regression method, that again has linear regression, support vector regression, Gaussian process regression, neural networks, and random forest again. And unsupervised techniques are that when you give the entire data, so it may have, let's say, whatever data you have given, it may have three different type of flowers, or it may have four different type of bearing defect. Like for example, there are total five classes it may have. Like one could be healthy bearing, and then you can have then after healthy bearing you can have mild bearing, and then you can have mild defect bearing, then you can have medium defect bearing, and then you can have severe defect bearing, and then you can have failed bearing. So there are total four classes which are in severe, which are in defect, and one healthy. So there are total five classes which are there. But before giving data, like we may not know that there are four classes, because the data is so high that it is very difficult for us to even know that there are four different classes. So basically we give all the data to machine, and machine itself or the algorithms itself figure out that there are five different classes, and in these five different classes these are the data which is over there. So that is basically called unsupervised learning techniques. So see how useful it is. See, for example, for the case of bearings, see, from the starting, suppose you are taking a bearing which is basically starting from the healthy state, and after, let's say, after 200 hours, or after, let's say, after 500 hours, the bearing becomes faulty, or bearing becomes defective such a way that it is no longer useful to use. So now you can easily identify the initial state that is healthy, and you can easily identify the final state that is faulty, because after it becomes faulty, machine itself stops, or something happens, some smoke starts coming from the machine, or some very strange noise start coming from the machine. So these two stages you can identify very clearly, but the other three stages, that is mild stage, or medium stage, or severe stage, they may be very, they may be continuous, like they may be next to each other, and it will be very difficult to distinguish between these. So in these kind of scenarios, unsupervised techniques are much better, because they define the stages and then they divide the data. So in unsupervised techniques, you can have K means clustering, K mediates clustering, fuzzy C means, and dimensional reduction techniques like PCA, that is principal component analysis, KPCA, that is kernel principal component analysis, isomap, and diffusion map. And what is reinforcement learning? So reinforcement learning is like it is again, so this is all mimicking human behavior. So you may have seen that there are some students who understand, like from the student's perspective, if you see over here, there are some students who will understand how the system works, and they will figure out what is important, what is not important, and doing what minimum task will give you the maximum output. And that's exactly what is that reinforcement learning is doing. So it is over here you are kind of maximizing the efficiency. You know that these are the bare minimum things that you should do, and that bare minimum things will give you the maximum output. So that kind of thing, if machine figures out, that is basically reinforcement learning. That's the idea. So that is, I have discussed something about AI and ML. Let me discuss something about bearings, and then I will discuss something about health monitoring, and then we will try to connect all three. So then, what is a bearing? So bearings, you may have seen so many shafts, or so many rotating components. For example, if we talk about grinding machine, if we talk about if we talk about any motor, or anything which is basically rotating, any shaft, any rotor which is rotating. But all these shaft, rotor, grinding machines, they are all has to be kept on ground. So basically, there has to be a structure, and that structure which is kind of attached to ground is stationary. So you have, like for example, in grinding machine there is a shaft which is basically rotating, and on the end of the shaft there is a tool which is doing the grinding. But this has to be kept on ground. No, so basically there is a, it has to be, it somehow has to do inside something, so such that the outer layer, that is basically called housing. So the machine housing has to be stationary, and the shaft has to be rotating, and there should be something between this that let it happen, and that something is bearing. So bearing is basically, it takes the dynamic loads. So what is dynamic loads? So the term dynamic itself means that changes with time. So basically, dynamic loads means the load itself will change with time, like over a period of time the loads will increase or decrease, and that is the idea over here. So bearings you will find in 90% of the rotating machines. Bearings will be something which is you can find almost everywhere, and you can find bearings from small machines, like for example, if you take out a drawer from your table. So many of us are having this drawers, no, in our table, which we take out and we'll keep something inside and we'll push it back. There is a small bearing. It's next time you pull your drawer out, you can see there is a small bearing over here that is kind of helping you to convert that motion, that is basically to smooth motion, that is linear motion that you are doing over here. To smoothize it, there is a bearing over here. Now you can talk about rockets, you can talk about wind turbines, you can talk about bigger things. There also find bearings. In smaller things, you can talk about roller skater. There are children who are rotating, who are basically like who are running on the road with that roller skater. That also has a bearing inside. So bearing is something which is ubiquitous in nature. You will find in smallest things, you will find in biggest things. So bearing is very largely you can find almost anywhere. And the prop, so now the thing is, the bearing is very modest in per se, like the cost of the bearing may be very little, like maybe 100 150 rupees in a smaller application. Even if we talk about the bigger applications like grinding machines or like lathe machine and all, you may find that the cost of the bearing, maybe even the special bearings, like for example, which is basically precision bearings and all, that cost also maybe 50,000 rupees per bearing. And if you are taking a spindle and you're putting six bearings in it, the cost of the spindle maximum can be 5 lakh. And this cost of the 5 lakh of the bearing you're putting in a machine, for which machine cost is somewhere around 5 crore. So for example, if you talk about grinding machines, in grinding machine the machine cost is 5 crore and the bearing spindle cost is only 5 lakh. So you kind of compare, in comparison to entire machine, the cost of the bearing is modest. That's what I'm saying. But what happens, this grinding machine may be put in a in a industry where this grinding machine may be kind of doing grinding for 10,000 motorcycles per day, and the cost of the motorcycles which it is machining per day, that may be in crores. So basically what happens, when you when a bearing goes wrong and when something happens to the bearing, then the entire production of the that particular day stops, and therefore the losses of the production, it becomes in crores. And therefore the bearing health is very very important. Basically health of the bearing, and we have to ensure that the diagnosis and prognosis models are good. Now what is diagnosis, fault diagnosis and prognosis, that I will define. So many of you may be aware that what is fault diagnosis and prognosis, but I will define them properly, that these terms are called diagnosis and this term is called prognosis, that in couple of minutes I will define. So earlier what used to happen, that because it used to have lot of data in bearings and all, and normally if you are aware from the, if you have done some in bearing field, so basically what happens, we acquire data at a very high frequency, high sampling frequency, that is 50,000 samples per second and all. So in each second you are having 50,000 samples, and that basically means that if you are kind of taking data for the entire life of bearings, you may be filling the your hard disk will be in terabytes and all. So in those kind of things, sometimes the data processing takes a lot of time, but with AI and ML, these things are kind of becoming more and more easier. Now again, to give you perspective, so still I have not started what is bearing health monitoring. I'm just trying to give perspective. So this is a graph which is basically many of us has seen maybe in third year of BTech or something like that. So you can see over here, there are three portions of it. The first one is called wear and failure. That is basically infant mortality also it is called. This graph is, the name over here is bathtub curve. And bathtub curve is something which is kind of very famous, and most of the mechanical engineers come across it in some way. So you can see over here the first portion over here which you're seeing over here, that is called infant mortality or wear and failure. That happens because of some manufacturing defects. So for example, poor welding, poor workmanship, or you have some material that itself is defective. So all those kind of things will eventually result in this particular portion over here, that is wear and failure. And in this what happens, you see hazard rate decreases. So once this gets over, the life of the component will actually increase. So for this portion which is this wear and failures, we can't do much by using whatever bearing health monitoring we are doing. Now same way is this random failures. So random failures can happen. So it is like accidents as far as human life is concerned. So for example, so if like for example, if there is a person who kind of takes care of his health and he goes to doctor every month and records his diabetes and records his sugar levels, sugar values, and his cholesterol values and everything, but recording his sugar values and cholesterol values will not help us decide that whether this person will die in a car accident or not. Same thing over here. These are random failures. So for example, electronic items, they typically follow this random failures kind of phenomena. So even if you monitor a bulb, then you can never predict whether the bulb will fail today or will fail after 10 years, because it is entirely random. Now, The last zero, that is wear out failure, in terms of human life, it is like old is and all. In terms of mechanical components, it is some kind of wear. For example, you may have mechanical wear or electrical wear or joint electromechanical wear kind of thing. And because of the wear, you can quantify the wear, and based on that, you can somehow predict the life. In case of humans, what you can do, you can basically say that as the person's see, as the person's age is increasing, there will be certain parameters which will be almost coming down, and eventually it will become zero. So that is kind of idea over here. So whatever bearing health monitoring or condition monitoring that we are talking about, that is only possible for this wear out failure over here. That is this particular portion, last one over here, and we are discussing only about that. Now there are couple of maintenance that can happen. The first one is called corrective maintenance, the second one is called preventive maintenance, and the last one is called condition based maintenance. So whatever we are going to discuss today, everything is condition based maintenance. But what is that? What is these definitions of these three that I will discuss briefly? So corrective maintenance is, see, basically if you are having a shop floor, and let's say you have 100 tailors, and these tailors are sewing shirts. Now each sewing machine cost is, let's say, 10,000 rupees. Now you have 100 sewing machines, and each machine is 10,000 rupees. Now hiring a maintenance engineers who basically puts oil in all this machine, who takes care of all these things, may be a little bit costly. So what could be an easier thing, because you have to pay the salary and everything for that maintenance engineer. So what could be easy? So easy could be that you purchase 5 extra machines. So you already have 100 machines. You additionally you purchase 5 extra machines and you leave it over there. And as soon as one machine fails, then immediately you shift that tailor to the new machine. So this is called corrective maintenance. So this is corrective maintenance is that when a machine fails, then you are kind of repairing it. So you have already utilized the full life of the machine. That is what is corrective maintenance. What is preventive maintenance? So preventive maintenance is, now I cannot suggest the same thing for grinding machines. I cannot say that suppose there are 5 grinding machines which you are working with, purchase one extra grinding machine and keep it with you whenever one fails you use it, because the cost of the grinding machine is, let's say, few crores rupees. So it is not possible to purchase one additional grinding machine and kind of use it as a spare. So there, what we do, we kind of put some kind of maintenance scheduling, and we say that every 6 months or every 1 year we will be doing these activities, and by doing these activities, we kind of reduce the maintenance. That is basically preventive maintenance. But in preventive maintenance, what happens? Because you are changing the component every 6 months or so, you will reduce the probability of failure, but you cannot make it zero, because there might be some component which may fail within that 6 months itself. And the component which you are changing, what may happen, suppose the bearing life is 10 years, but you are changing it every 6 months. So what may happen, you have changed a bearing after 6 months which life was actually 10 years. Now you have put a new bearing which life is only 3 months. So you are changing a good component with a bad component. That is also possible in preventive maintenance. However, so these kind of things may happen in preventive maintenance, but most of the industries nowadays, they follow only preventive maintenance. What is condition-based maintenance? So condition-based maintenance is, we put multiple sensors, and we kind of take the values from all the sensors, and based on that we kind of see that there are what is the status of the component, and slowly we kind of replace the component only when it is defective. So this is what I am suggesting. So this is what we are doing. We are putting multiple sensors, and we are recording some values, and we are putting some thresholds, and whenever it crosses a threshold, we say now it is about to be defective. A simple example I will give. Suppose you purchase a new scooter. So when you purchase a new scooter, it will be very smooth. There will not be any sound. There will not be any. There will be very less engine sound and very less engine vibration. But if you keep on running it without any servicing, without any taking any care, what may happen after 1 year? It may have huge sound, and it may have huge vibration. So suppose you are recording only sound or only vibration. That's what you can consider over here. That these blue color values, it could be either one of that. It could be either sound or it could be either vibration, and that is what is degradation parameter. So it could be any parameter which degrades with time. So you are saying you are plotting something which degrades with time, and when it crosses a particular threshold limit, you say now it is about to fail. So that is what eventually we are doing, but in a much evolved way. So that's the idea over here. So still I have not discussed what is diagnostics and what is prognostics, and how these are part of
condition monitoring or health monitoring. So what happens, suppose you go to a doctor, or a person goes to a doctor, and doctor takes the data from the person, and he kind of measures the temperature and sees everything and sees the tongue and all, and takes the blood sample and does some test, and doctor says, okay, based on these things, whatever test I have done, you may have this particular disease. That is, you may have, let's say, you may have flu. That is, you have only you have just some cough, and that's all. You will recover in 5 days. So that's all. So doctor has taken some data, and based on the data, doctor is saying what is the current status. That is basically diagnostics. In terms of machine, you take the vibration of a machine, or you take current signal of a machine, or you take some other signal of a machine, and based on that, you say that now there is some defect in this machine right now, or machine is healthy. Something, either bearing is healthy or bearing is defective, something like that. That is basically diagnostics. It has three parts. That is fault detection, fault isolation, and fault identification. What is prognostics? Prognostics is, suppose you are employed in a company, and company is very kind of very liberal, and it gives you yearly checkups, yearly health checkups, and that company has maintained one single doctor who takes all your checkup, and every year he checks up your sugar values, your cholesterol values, your blood samples, and everything he properly maintains. And every year he puts a new so he maintains a dot, he maintains charts, and every year he plots that sugar values and cholesterol value in that. And suppose your cholesterol values or sugar values are increasing with time, then doctor may say, see, you are sitting now, you are doing a sedentary job, you are not running or you are not working properly. So if you keep on doing it, if you do not change the operating conditions, if you keep on doing it, you may have this disease. So that disease will have not happened right now. It is only a prediction. It is only something which is kind of mentioned. It is only a prognosis. That's what it is. Prognosis. Prognosis means future predictions about life or failure. So if you change your operating conditions, for example, if doctor mentions that this is going to happen, and if you suddenly change, you start waking up early in the morning, you start going to walking and running, and then what will happen next year? Your diabetes will come down, your sugar values may come down, and then whatever doctor has said, that may not happen. Same thing is applicable for machines also. So for example, you may be running at a very high load and very high speed, and then doctor says that if you keep on continuing, and then you basically take the vibration and you say that if I keep on running on this speed and this rpm, then basically this speed and this load, then this bearing will fail in another 1 year. Then suddenly you think, okay, I don't have money to replace the bearing, or I don't want to do all those things. Let me run on a smaller speed and a smaller road. So if you start running on a smaller speed and a smaller road, instead of failing in 1 year, the bearing will fail in another 10 years. So just by changing the operating conditions, you have changed the life. That's what is prognostics. Condition monitoring, by now you have understood what is condition monitoring. And so basically you need a lot of data in structural health monitoring and condition monitoring. You can use vibration, you can use pressure, you can use temperature, you can use lubrication oil, you can use motor current over here, you can use performance monitoring. What is performance monitoring? So in case of grinding machine, you can say that now, so for example, you have a grinding wheel and you're doing the monitoring, and you're saying that earlier, whatever, when I used to machine, all the components had this RA value of 1.6, but now last two components RA value has become 2.5, and now this last component that I have taken, RA value has further worsened, and therefore since RA value has further worsened, there is something wrong with the wheel. So that is performance monitoring. You are not capturing vibration, you are not capturing pressure, you are not capturing sound. You are taking the component production values, and you're capturing something which is related to performance of the machine. So now what happens in many machines, it has been kind of established that vibration sensors works out to be the one of the best sensors. The reason is it is very cheap, and it is very rigid. It doesn't get affected by the operating conditions. And normally what happens, the other things like environmental conditions like temperature, humidity, and all, they do not affect the vibration sensor oscillator much. And therefore in most of the machines, typically vibration sensors is used in the. So this is one of the tests which I am showing you over here. That is, this is actually my test is from my PhD, and you can see there are a number of sensors over here. Actually there were 5 sensors over here, and you can see all these different color of wires. Because sensors are mounted inside, that sensor cannot be shown in this picture. But the idea is that I had this temperature sensors, PU probe, pressure microphone, accelerometer, and current probe, all that were over here. So the idea is that you have all this and then you're monitoring. That's the idea. So typically what has been established that vibration sensor is one of the best sensors, and whatever we are going to discuss in the remaining discussion, we are only talking about vibration sensor. And now what I'm going to discuss that how do you do bearing health monitoring. So now I'm going to discuss about how do you do bearing health monitoring, and in different portions of it, I will kind of keep on mentioning that what is AI and ML and how to basically take like what is that AI and ML that is basically being used over here. So I am discussing bearing health monitoring, and whenever there is something related to AI and ML, I will kind of point it out. So what has been done? So basically, if you talk about AI and ML, there are number. So basically, there are number of things which you are doing. That is basically. Uh, so I hope sound is clear. Okay, now everything seems to be working. Yeah. So let me go back. So if you talk about bearing health monitoring, what is happening? There are number of things which you can do. One, you can do some kind of classification. What is classification? You can classify whether bearing is healthy or bearing is defective. That is one. And you can classify whether bearing is having outer wrist defect, or whether bearing is having inner wrist defect, or whether bearing is having some other kind of defect. That is classification. Classification comes under machine learning. Also, you can do some kind of regression or some kind of prediction or some kind of segregation. What is segregation? So you can see this. Okay, let me show you over here. This is the entire. Okay, let me show it somewhere. This is the entire life of the bearing. So you're seeing this. What is this being shown over here? That is the data which is taken from a rig, and this rig basically this is established at IIT Madras. This is a rig over here. So what we are doing over here, we have some accelerometers and we have a motor, we have a variable frequency drive, and we load different loads over here, and we basically kind of take data with the help of this deck card which is over here, and with the help of deck card we kind of find out this estimated data over here. And now what we do, so initially for classification, because we need to make different classes, and therefore for making different classes, what we do, we take a healthy bearing and we take the data, and then we take some defective bearing, and in these defect we are kind of creating manually, and therefore we are calling it CD defect. So what we do, we create some outer wrist defect, we create some inner wrist defect, we create some ball defect, and that is what is CD defect. And sometimes we take a combination of it. So for example, if you see the over here, it says CD defect data with various fault types, and therefore there are combination. What is the combination? You combine inner race and ball defect, you combine ball and outer race defect, you combine inner and outer defect, and you combine all three defect. So basically there are total 8 type of defective bearings which kind of over here other than healthy, and that's the idea. And in this also you can take different severity. For example, outer race defect could be with 0.5 mm defect, 0.75 mm defect, and 1 mm defect. Same way inner race could be with 0.5 mm defect, 0.75 mm and 1 mm defect. Same way with ball defect could be 0.5 mm defect, and that's the idea. So this is, you are creating different classes, and then you can do classification over here. That's the first level. What is the second level? Now the classification is not much of the use as far as industry is concerned. See, if you go to industry and you tell them there is an inner race defect, it doesn't matter much, because they don't bother what kind of defect it is. As long as there is some defect, that's all. They have to change the bearing. So the type of the defect or classification of defect is not a very useful activity as long as the industry are concerned. But to start with, to basically point it out, we have to, this is the first step basically. So we kind of start over here from the classification, and then we go for something which is segregation. So what is segregation? Again, it is something which comes in machine learning. So for example, you take a bearing and you run that bearing from the healthy condition that is over here, and you keep on running it, and you keep on running it, and then you find out over here it fails. Now if you see this entire data, that is 1000 minutes data, and it is estimated like this. So basically what is the idea over here, that in normal operating conditions bearing may not fail in 1000 minutes. So what has been done, we have put very high load, that is 9.9310 newton, that is 930 kgs. 931 kgs load has been put over here, and the bearing has been run at 2800 rpm. Imagine that 931 kgs load has been put over here, and with that load it has failed in around 1200 minutes and all. That is 20 hours. So now if you have something like this, now if you see it, if a human mind sees it, so that person can simply say that okay, maybe from here to up to here it looks somewhat healthy. So there is hardly anything, just by looking at it, Just by looking at it, a human can say that okay, maybe from here to here it is healthy, and maybe from here to here where you have some kind of slope, but it is still lesser than the final value. Maybe from this point to this point, maybe it is mild defect, and then maybe from here to here it may be medium defect, and suddenly it increases, then it is severe defect. So just by looking at it, I can somehow have multiple classes, multiple segregation. I can segregate it in different portions, and that is what is segregation. So that is another activity that can be done over here, that is basically done in bearing diagnostics and prognostics. That is, you are saying that bearing is having mild defect or medium defect or severe defect or healthy, something like that. And the last one is prediction. So prediction, so I will come to denoising. What is prediction? So prediction is that you kind of say that, like for example, at this time instant, suppose you are at this 600 hours, and if you ask me what is the life of the bearing, so actually based on this I can't say anything, because till now there has been no increase. Till this point, there is no increase. So even if you ask me also, I may not be able to answer it very truthfully. Other than I can use some kind of Beaver distribution and I can say certain things. But based on data analysis, I can't say much. But if you ask me same question over here at this point, then I can say something, because now I have this increasing slope and I can assume that vibration will be keep on increasing and somewhere over it will fail. Now if you ask me the same thing somewhere over here, then also I can say something, because now there is a change between this and this. I can say okay, it will fail in this much time. And if you ask me the same question over here, again I can answer, because I know that suddenly it has changed. There is a huge change. So that is basically prediction. So first you find out whether your bearing is in healthy condition, whether your bearing is in mild defect condition, or medium defect condition, or severe defect condition. And once you do it, maybe in mild defect condition and medium defect condition, you also need to predict how much life is remaining. You don't need to predict probably in the case of healthy bearing that how much life is remaining, because anyway it is healthy, you don't care anything much now over here. But probably in the case of mild defect, medium defect, and severe defect, you need to also predict how much life is remaining, and that also is done as a part of bearing prediction and bearing diagnosis and prognosis. These are the things which we are going to discuss today. So how normally we'll start? So see, now the bearing health monitoring in itself is a very broad field, and it is not possible to cover that in 1.5 hours. So certain things I am simply putting it over here just for information. So what happens, and that I will simply skip. This is not the main activity over here, but it is important for you to know. So therefore I am putting. But once the main thing will come, then I will explain in more detail. So first thing is denoising. So what is denoising? So you basically capture that vibration data, whatever you have captured, and then you find out the data which is relevant to your thing, which is relevant to this bearing defect. That only you kind of keep it, and remaining you scrap. So for example, if you are taking a data from a machine, now this machine may have a gear also, and gear also may be generating some kind of vibration. And now if I am predicting bearing life, this gear vibration data is not useful for me, because it is related to gears. I am only considered about bearing. So that gear data is noise for me. So if I remove that gear data, that is basically called denoise. So now when let's say you have already denoised and you have already found all the data which has information related to bearing, then what do you do with this? So now you can do number of things. You can process. So there are number of domains in which you can process it. You can process it in time domain. You can process it in frequency domain. You can process it in time frequency domain. So once you process in that many domains, you can have number of parameters. So for example, I am showing you over here a list of 72 parameters. Now which parameter you should? How do you know? You may be doing that you may be doing that bearing analysis first time. I have already told 72 parameters, and if you keep on reading paper, you will find that each paper is saying some new parameters. And if you take all the parameters, you can easily go to 100 parameters, 120 parameters. You can easily go. So which parameter to use? Which parameter not to use? So what is the stage right now? So stage is like this, that I have taken the vibration data and I have denoised it, and then I have found all the parameters. And these parameters are nothing but numbers. So RMS value may be 5 meter per second square. Crest factor may be 2.7. Peak may be some 7.2. So these are all numbers. So I have found these 72 parameters over here. But which one is important and which one is not important, that I don't know. Now for doing that, which one is important, which one is not important, we call something that is called feature selection. And for this we use a machine learning technique. And what is that machine learning technique over here? So basically there is a decision tree. So there are these trees over here. These are trees, tree 1, tree 2, and tree n over here. So what is happening? These are different conditions. These are different if and else.
So these are different if conditions. If this happens, then this is answer. If this happens, then this is answer. If this happens, then this is answer. And each tree is a decision tree over here. And this is the output of this tree. This is the output of this tree. This is the output of this tree. So basically, if we consider a forest,
So what is a forest? So a forest is basically where you have number of trees, and that is the idea over here. So we are talking about these decision trees, and this random forest, whatever we are talking about, it has thousands of these decision trees, and each decision tree is giving a decision. And then when we take the voting from it, we kind of take result one, result two, and result n, and we kind of say which result is coming in the maximum number of trees. That is basically is majority voting. So you find the result from all the trees and you see that which result is coming maximum number of times. That is basically majority voting, and you say that okay, this is the result which I will take.
Hello, sir.
And yeah,
These orange color circles are not result. Blue color circles are result. In
yeah, I
tree,
couldn't hear you. Can you repeat this?
in diagram tree 1, tree 2, tree 3,
Yeah.
the blue color circles are the result.
Yeah, so basically all these are if and else condition. See, blue also and yellow also. They're all if and else condition, but in different tree there are different outputs. So this blue color is what is chosen over here. So in different trees, the values which is written inside these circles, they will be different. They have, so in each, so for example, what happens? Okay, so what for example, what happens if I have to choose particular area? I can, like for example, I am choosing the area which comes in first quadrant. Okay, then I can say it should be more than x should be more than 0, y should be more than 0, and I can maybe I am capturing something which is within that x, within that 10 by 10 square. Then I can also say that x should be less than 10 or y should be less than 10. Now these are four different conditions. It's something like that over here.
Okay.
So everywhere you are putting different conditions. So nowadays, luckily, means because you have asked this question, if you want to learn about more, there are so many, means nowadays the access to the information is very high. There are so many YouTube channels which are presenting this lot of with lot of animations and all. It'll be very easy for you to understand if you want to understand that. So that from there you can easily understand. So we use this machine learning technique that is called random forest, and we identify the parameters which are useful. So for what happens? So we kind of take three different live sets. So whatever I have told over here, this is for one live data. This is for one live data, and we repeat it three times. We kind of do it three times. Why we do it three times, that I will mention later. So we repeat that live data for three times for prediction and all, and for that we apply this random forest. Once we apply this random forest for the first data set, out of 72 features, only 15 features are selected. For the second data set, out of 72 features, only 13 features are selected. For the third one, out of 72, 15 are selected. And you can see that there is an improvement in selected features, that this number is higher than this number, that's all. And also the time is less. See, if you are doing any calculation with 72 per features, it will take more time. If you are doing the same thing with 15 features, it will take less time. And therefore, obviously, there will be some reduction in time. And also, there is one more important thing is there is no overfitting. So, what do you mean by overfitting? That is this. So, if, like for example, if you take all 72 features and if you fuse it, that is you are doing data fusion. So if you take all 72 features and if you do data fusion, you are getting something like this. You see, this is not so good. For any kind of prediction, it is not a very good idea because it is at the same point it can assume any value. So if I do live prediction with this, that is going to be very, very less useful. But if I do the same thing by this, that is going to be much more useful. So this is after data fusion with 72 features, and this one over here after data fusion with 15 features, which I have selected from here. So that is overfitting. So if you are kind of selecting useful features, if you have taken only 15 out of 72, you have avoided overfitting. That is also an additional benefit which you are getting. So first of all, complexity is avoided because you are using less number of samples and all, less number of features.
And secondly, one more thing is that you have avoided overfitting. So these both benefits we get over here. And then again, so now, okay, so what has happened till now? Let me again come back. So what you have done till now, you have started with vibration data. You captured the vibration data, and after capturing the vibration data, you did denoising. That is, you remove the noise which is related to gears and other components. Now the vibration data is only related to bearings. And then what did you do? You did data processing and you found different features. So you found 7 features, and then you applied random forest, and after random forest you kind of listed them. You listed these 72 features in the order of importance, and then you chose 15 features. Now after that, even if you take any of these 15 features, you may get different results. So which features to take? Like you have 15 features, but which feature to take? Only the first one or the second one? You may take only the first one, then you may lose some information. Because you're taking only the first one, you may lose additional information. So what could be done? That you take all these 15 feature and you fuse it. That is basically called data fusion, and sometimes it is also called dimensional detection. So either you fuse it or you kind of choose only few important features out of this. That is basically dimensional detection. And data fusion is that you take all the features and you combine them in some method and then you use it. So that's what is we are going to do over here. So these are the 14 techniques which are in data fusion techniques, which are you may be probably heard of. You may have probably heard of these names. So these are first 7 among these. That is 1 to 7. They are linear techniques, and then 8 to 14 they are non-linear techniques. And these are the linear techniques which are used for data fusion, and these are the non-linear techniques which are used for data fusion. And that's the idea over here. So we are going to compare all these 14 techniques. I will show you the results, and all these 14 techniques can be used. So the idea is, but even if you use, so suppose you use all these 14 techniques and you fuse the parameter, how do you choose among these 14 techniques which one is better? So you have 15 parameters, and these 15 parameters can be fused by these 14 techniques. So you can take 15 parameters and you can either use PCA, or you can use ICA, or you can use MD, or you can use one of these, let's say LLE. But which one is the best? So for identifying which one is the best, I should find out some parameters, and I should judge on the basis of those parameters. And what are those parameters? So these parameters are, there are 4 parameters. These are monotonicity, prognosticity, trendability, and simultaneity. What is monotonicity? That should be continuously increasing. See, I can predict better if I have something like this. I can predict better if I have something like this. That is either monotonicity increasing, like continuously increasing, or continuously decreasing. But it is very difficult to predict if I have something like this. So that is what is monotonicity. So monotonicity for this and this is probably close to 1, and monotonicity for this will be probably close to a zero 0.5 or zero 0.2, something like that. So if you have higher monotonicity, it is good, it is better. So I should choose the parameter which is giving me something higher monotonicity. That's the idea over here. What is the second one? Second one is the prognosticity. What is prognosticity? See, the bearing is failing between this value over here, this y value, and there is a upper y value and there is a lower y value. And if it is very very small, so for example in this figure, suppose all the bearings are failing between 220 to 230, then it is very easy for me. I can make a rule that whenever it will cross to 220, it will fail. It is easy for me. But suppose one bearing fails at 200, another let's say the integration parameter is RMS. Let's say one bearing fails at 200 meter per second square RMS, and the second bearing fails at 500 meter per second square RMS. The third bearing fails at 10,000 meter per second square meter per second square RMS. So how do I say that which is the level at which bearing will fail? That will be very difficult, and therefore this prognosticity. So if all the bearing fails between a very small interval, let's say 200 to 220, then I can easily say that whenever it will cross it, it will fail. That is what is the prognosticity. And what is trendability? So let's say you are having some kind of trend. Like every time if you have a different trend, it will be very difficult to do trend evolution. For example, let's say this picture over here, which I showed you earlier, that is trend evolution. Let's say you have this. If every time, like if you're doing for first bearing, and if you're doing for third bearing, if you're doing for fifth bearing, if every time you have something like this, it is easy to predict. Let's say first time you have this, and second time you start to have something like this, third time you start to have sudden something like this. It is difficult to predict, and that's what is trendability. That's what you see name over here, trend evolution, and that's what is that parameter which is called trendability. So if trendability is good, it means every time you will have something similar. And what is signal to noise ratio? Signal to noise ratio is that whatever you are capturing, in that signal is more and noise is less. That's the idea. Now these four parameters are important. So these four parameters, what is done? These four parameters are clubbed, and for clubbing that we are using some kind of weighted sum. So you can see that M is over here monotonicity, T is permissibility, T is trendability, and SNR is signal to noise ratio, and these are the weightages. And so basically we kind of optimize it and we find this weightage, and then we use our techniques and we find that. So we want to compare this 14 techniques. So we want to find which among that has the highest fitness value. So this is how we are defining fitness value, that is H over here, that is health index over here, or H over here, and that is a weighted sum of monotonicity, permissibility, trendability, and SMR. And what I am doing is I am trying to maximize it. So see, if I am comparing this 14 techniques, the input is same. The initial 15 parameters, the initial 15 parameters that I am supplying to these 14 techniques, that remains same. There is no change in that. The initial 14 parameters, whatever the initial 15 parameters that I am supplying, that I am getting after that random forest. See, initially I applied random forest and I got this 15 parameters over here. These 15 parameters I am supplying to all 14 techniques, and I am comparing their health index. So whatever has the highest fitness value, that is the best technique. That's what has been done over here, and we have found that LLE and LTSA are the best. Once again, I will show you over here. So for example, these are those three tests which I was showing you earlier. So let's say this is first life test, this second life test, this third life test. This is first life test, this second life test, this third life test. And this is, what is this line over here? That is after data fusion by PCA. So whatever line you're seeing over here in this curve, that is after data fusion by PCA. Whatever you're seeing over here, so input same for all these three, input same for all these three, input same for all these three, input same. But you're using PCA, ICA, and FA over here. These are linear dimension detection technique. Now you can easily say that if I use, you can easily say it, even if I would not have defined monotonicity and all, you could have easily told me that, see, using this which is FA over here is bad, using this which is PC over here is better. So that is what we are doing it. So we are finding over here now, if you see over here FA, you see FA over here, you have fitness value of 0.251, and if you see PC over here, you have fitness value of 0.551 over here. Same thing would have seen from here. Now to quantify that, whatever we have done earlier, that we have defined monotonicity and permissibility and trendability and signal to noise ratio, that we have done to avoid this human intervention. Now over here I have to see everything. Now it is very difficult for me to compare between this PC and ICA. They're almost same. You see this one and this one, almost same. But if I use some kind of mathematical tool as I have defined earlier, I can say, see over here 0.551, it is 0.557. So I can say ICA is a bit better than 0.551, which may be difficult for me to say if I am judging it manually. Now these is for linear techniques. Now same way if I do it for non-linear techniques, again I can say, you can see over here, again I can say that this TSNE, you see over here, how much variation is there? That is probably not good. And LLE and LTCA are probably good in comparison to TSNE. Same thing as I kind of mentioned earlier. And now what is done over here? Some kind of plotting is done. So what we are doing over here, we are getting PCA1, that is the best output of PCA, and PCA2, that is the second best output of PCA, and we are plotting it. Now ICA1, that is the best output from, that is the best feature from ICA, and ICA2 is the best feature from ICA2, and we are plotting, and we are seeing how far are they. So you are seeing there were 8 classes. So it is kind of classification which you can visualize. So there were 8 classes, and what were those 8 classes? Those were healthy, ball defect, inner race defect, outer race defect, inner race, and all these kind of things were there. Now again, if you like, as I mentioned again earlier also, that if you apply human mind and if you ask which one is better, anyone can probably tell that this is not as good. Like MD is not as good as LDA over here, or MD is not as, or LPP is not as good as LDA over here. But now again, instead of me seeing it manually and I am telling you, okay, this is better, you see there are different clusters over here, but they are overlapping over here. If I have some kind of tool which does it for me, that is what is the idea of artificial intelligence machine learning. No, so for this so that is same thing we are doing for non-linear techniques. So this over here is linear techniques. This over here is non-linear techniques, and for comparison, we use these techniques which are Bhattacharya distance and KLD, that is Kalbeck-Leibler divergence, and this basically finds out the distance between different distribution. So over here, what I am assuming that each cluster, so each cluster which you are getting over here, that comes from different distribution, which is a correct assumption, because one is from healthy, one is from ball defect, one is from inner wrist defect, one is from outer wrist defect. They are different distributions, they have different properties, and therefore they may have come from that. And if I kind of compare them, then I can clearly see that if I kind of compare this Bhattacharya distance and club distance, I get this. Over here I find that LDA is best over here. You see, LDA comes out to be best from LDA also, and from BD also, and from KLD also. And same thing I was saying here also. You see, this is LDA. I can see here itself that it is much better in comparison to others. Now here I can say MD is very bad. You see over here, MD is bad, LPP is bad. Let me see the value over here. So MD, see the value is very small, 12.5, while this value is 52.5. So the distance between the clusters, what is this Bhattacharya distance? So Bhattacharya distance or Kalbeck-Leibler divergence, they are the distance between the clusters. The distance between the clusters is 52.2, which is higher in comparison to 12.5, which is lower over here. So that's the idea. So whatever we are able to do manually or using our brain, that we need to use some kind of machine learning techniques, and we should identify. Now the segregation portion that I was saying. So for that we have used PELT over here. This is the mathematical portion. As I am not going into any mathematical portion in this lecture, I am only showing you the results so that you can get the overall idea. Yeah, any doubts?
Excuse me, sir. Sir, the Bhattacharya distance is one parameter to know the whether the out of protein models techniques, some techniques are better. So you are saying that the distance is the parameter there.
So it basically counts the distance between two clusters. So let's say it is one cluster over here. See, let us see this over here. Let's see this one over here. This is one cluster, and this is another cluster, and you see the distance between this.
So
Okay.
that is the criteria, sir, to decide.
Yes, that is the criteria. If they are very far away, they are better classified.
Okay.
If all the clusters are very far away, there is no common portion, they are better classified. Now if you see over here, the distance between this and this is almost zero. The green color and the purple color over here. But the distance between pink color and green color over here is very high, but the same distance over here is hardly anything. So this is not better classified, but this is better classified. That is what we are doing with Bhattacharya distance and Kalbeck-Leibler divergence. Clear?
Yes.
Okay. So now we are discussing about that segregation that I mentioned. So for example, what happens? How do you say that whether you are in mild stage or whether you are in medium stage or whether you are in severe stage? So what we are doing over here, we are using PELT. PELT is an algorithm which kind of divides a time series into two different portions, which says that up to this portion it is different, after this it is different. And to prove the algorithms, we have used it on 8 different data sets. So you can see over here, this is what is the result over here. So it says that it is health line over here, and it is medium stage over here, it is severe stage over here. Like that it is dividing. It is healthy state over here, and it is mild effect over here. Component is healthy because it is still healthy, but depending on what is the criticality of your system. Let's say you are kind of, you talking about a bearing which is in a nuclear power plant. So for a nuclear power plant, you probably don't want a winter bearing to be in mild state. As soon as healthy condition leaves, you kind of probably want to remove it. But let's say you're talking about a bearing which is in a swing machine. You probably don't care what will happen even if it fails also. So you can let it run up to severe fault also. But for that, this is the damage stress identification. That is like segregation. And this is a machine learning activity which is done by this PLT algorithm over here. So that's the idea over here. This is being shown for different kind of thing. So be like over here, because see this what happens. This PLT defines different kind of stages. This says that it is this is stage one, this is stage two, this is final stage. PLT doesn't know whether it is healthy or whether it is mild defect or whether it is medium defect. So the problem is severe is very easy to identify because after severe it is anyway failing, and healthy is also very easy to identify. So but the mild and medium are difficult to identify, and that's why we have kind of come up with an algorithm which kind of, this is algorithm, I'm not going in detail, which kind of finds out the range, and it says that if you are between 6, that is 6 over here, and 35.6 over here, then you are in mild stage. And if you are between 28.8 to 66.6 over here, then you are in medium. So you can see there is some overlap over here. See, that overlap will always be there because you're talking about something which, for which you cannot remove the bearing. See, all this whatever you're doing on the basis of vibration data. You are not taking out the bearing, you are not taking out the bearing, and you are not measuring the defect. So you can never say whether it is mild defect or medium defect. So you are only measuring the vibration data, and on the basis of vibration data you are saying something, and therefore there has to be some kind of overlap, and that's what you're seeing over here. Now there are other methods like support vector machine and all that also can be used for classification, and that's what we are discussing now. So for support vector machine, how do you use support vector machine for classification? So support vector machine is very widely used. What it does, it basically finds a plane, and it finds a plane which is called a hyperplane, and it finds a plane in such a way that distance between two clusters is maximum. For example, if you see over here, what you're seeing over here, I can divide this by multiple lines. So for example, I can choose a line somewhere over here. Let's say I can draw some horizontal line over here. But with that horizontal line, I will not be able to divide it perfectly because there'll be so many points will be over here, which will be black, but that will be classified as red. And there'll be so many red points over here, which will be classified as black. But if I draw that line over here, there is only this one point over here. There is only this one red point over here which is classified as black, and there is no black point which is classified as red. So this is the best line, this is the best plane, and to choose the best plane is done by support vector machine. That's the idea about support vector machine. Now many things you cannot see in 2D, and therefore for that you kind of project them in a higher dimension. So you project this 2D in higher dimensions, and then this line becomes a plane, and then you go for a better plane, and that is basically called kernel based SVM. So that's the idea about it. Now how it is useful for bearings? So in bearings you can differentiate between fault types and severity types. So over here what you're seeing over here, that is kind of differentiating between only fault types. So you have healthy bearing, you have a ball defect, you have an inner resist effect, and you have an outer resist effect. And initially you train with SVM, and then you use support vector machine. And if you do that, you can see over here, you're clearly seeing that all 100% accuracy you are able to identify that which one is ball defect. So this one healthy is level 1. So whatever you are having over here, all these are healthy. Ball defect is level 2. So whatever you are having over here, everything is ball defect. And this is inner resist defect you are having as 3 over here, and outer resist defect you are having as 4 over here. So that's the idea, it is 100% classification. Now over here, both type and severity are combined. So you see, healthy, and this one over here is inner resistivity with 0.5 mm. This one over here is inner resistivity with 0.75 mm. This one over here is inner resistivity with 1 mm. So both type and severity are combined, and again classes are made. And over here, it is not as good as earlier over here. You can see the labels over here. For example, if you say the label over here, healthy is 1. So out of healthy, there are 10 healthy components, out of which 2 are wrongly classified. These 2 are wrongly classified, and therefore accuracy is 80%.
Hello,
Again over
sir.
here in number 3, there is one component, there is one sample which is wrongly classified, and therefore you can see accuracy is 90%.
Hello, sir.
Yeah.
So, what is the meaning of IRD 0.5 mm, IRD
Yeah,
0.75
good.
mm?
Yeah. So IRD means inner raised effect, and ORD means outer raised effect. But inner raised effect can have different severity. Like for example, there could be one inner raised effect where the size is only 0.5 mm. That is size. Defect width. 0.5 mm is defect width. 0.75 mm is defect width. So if you are having IID 1 mm, that is a high severity, and if you are having IID 0.5 mm, that is low severity. And that is important because if your severity is high, that means your bearing is in severe defect kind of condition. If your severity is low, that means you are in mild defect kind of condition. So you are kind of doing classification for both type, What is type? Type is healthy, inner ridge defect and outer ridge defect. What is severity? Severity is 0.5 mm, 0.75 mm and 1 mm. Is it clear?
Yes, sir.
So these are the different labels over here, and that's what you can see. There are 7 labels, and that's how it is shown over here. Now, coming to this over here, whatever I showed you earlier, that I can plot PCA1 and PCA2. So I have plotted this KPCA1, KPCA2, isomap 1, 14 techniques. That's what I have done earlier. And then I did that BD, that is Bhattacharya distance, and KLD, Kalbeck-Leibler divergence over here. Now I could have used SVM here. Same thing I would have, instead of plotting this like PCA1 and PCA2. You can visually see it over here. In SVM, you cannot see it visually in such a proper way. In SVM, you're only getting whether it is, in SVM, you're mathematically getting it whether it is inner raised effect or outer raised effect. Here, you're able to see it visually. Yeah. Yeah. Can you please repeat? Sir, I couldn't hear you. Can you please repeat?
Sir, probably he just opened the mic, sir. So you please continue, sir. Hello.
Yeah. Hello.
Yes, sir. You can proceed, sir, because some participants just opened the mic. Because of that.
Okay. Okay. Okay.
Yes,
Okay, so this is so now I will use SVM that. So you can see over here, this is what is SVM has been used over here, and you can see SVM linear, SVM poly, and SVM RVF. This linear, poly, and radial basis function, they are called kernel. So you are kind of seeing them in higher projections, and you can see that SVM is also able to identify 100% for 7 method. So you can either do it by Bhattacharya distance, or you can do it for BD, or you can do it by SVM. See here also you are saying LDA is best. So you are doing it by SVM, but you are saying 100, 100, 100, and LVM is able to. So LDA is best here also. So it doesn't matter whether you're doing for BD or KLD, or whether you're doing for SVM. You're always getting the same technique as the best. So now we have covered classification and we have covered the segregation. Now the last thing which I want to cover is basically prediction. So you have run 3 bearings and you have failed them. And now you are taking a fourth bearing, and that fourth bearing you are running, and you want to predict the life of the fourth bearing. And for prediction, what happens? See, if you type nowadays, every one of us typing in WhatsApp, right? Or any other software also. So for example, there is this word is. So now this word is, that is is. So since we are typing, sometimes WhatsApp will suggest us like which word to be use. So and it is many times it is very very accurate. So for example, if I'm writing, for example, if I'm writing I am going there or I am doing it, after I, WhatsApp will never suggest is. And so it is not that WhatsApp or these algorithm rule know the rules of the grammar. It is on the basis of the memory that they are suggesting. They are saying that every time, see, whatever words you're using more frequently. For example, let's say we are from different region. One is from Tamil Nadu, one is from Telugu region, or Andhra Pradesh region, something like that. So if a person who is from Andhra Pradesh, if he is typing some certain words, like let's say there are some Telugu words, but he is typing in English, and same way a Tamil person is typing Tamil words in English. So those Tamil words also, or those Telugu words also, will be suggested by the WhatsApp. So obviously they are not written like that in English. They are Telugu words, but they are being typed in English. They are not English words. But just by the use of it, just by because that person is using it again and again every time, that they are being suggested by this algorithm. That's what is long short term memory. So it retains in long term also that this person used this particular words in this kind of things, and it also retains the application. For example, it will also give you, like for example, if you're saying I am going somewhere, I am living somewhere. So based on the context of the sentence, it will give you a proper word. So that's what it is called, long short term memory. It is kind of a prediction technique, that what is going to be used, what is going to happen next. So for example, in case of WhatsApp and other thing, that's what I was mentioning. It is kind of prediction that what word you are going to use next. And you start typing in some chat thing or something like that, and you will find that most of the time it is correct. Whatever words we are looking for, it is there. And many times we don't have to type even a new word, everything will be there. So for example, if I write I am writing, it will suggest email. So that kind of thing I am saying, that is a prediction. It predicts that I am right, after I am saying I am writing, I will probably say email. That is what is the prediction over here. So that long short-term memory we have used on the output of that 14 techniques that we mentioned earlier, PCA, ICA, MD, and all, and we trained entire thing, and after training we have found what is the error. So this is the training over here. So now you see there are some techniques over here for which prediction and actual are very very close. For example, this one over here is LTSA based, and this one over here is LLE based, and for that you can see the actual and prediction are almost same. There's hardly any error. But out of the same 14 techniques, some techniques did not perform very well. Some techniques performed very well over here, but some techniques did not perform very well over here. For example, you see LDA was performing very well in classification. You see over here, in classification, LDA performed the best. All 100 over here. Even here 100 99.8 99.5 and all, and everyone else is 90 85 over here, 99 over here. So for classification, LDA is the best technique, but LDA is not the best technique for prediction. And for prediction, LLE or LTS is the best technique, and that's what you're seeing over here. LTS is this one over here, hardly any error, or this one over here, hardly any error. But if you use TSNE, you have lot of error, or if you use FA based over here, you have lot of error. And this is what is the prediction. So I am predicting the remaining useful life, and I'm comparing with the actual. So what is RUL? RUL is remaining useful life. What is that remaining useful life? So suppose, let me start. Oh, okay, let me start over here. If you, let's say, life of this bearing is 1050 minutes into 10 minutes, and if you ask me over here at that 600 into 10 minutes, what is the life? And if I say life is 450 into 10 minutes, and actual life is also 450 into 10 minutes, then I'm 100% correct. That's what I'm doing over here. If you ask me at 800 what is the life, then I know what is the life, because I know this is 10, this is 1000 over here, this is 800 over here. I can minus that. That is the actual life. And if my predicted life is same as actual life, then I'm 100% correct. And that's what I'm showing over here. So I'm comparing my predicted life with my actual life, and that's over here. I'm predicting actual life and prediction life, and that's what you're seeing over here. They are kind of matching over here. They can be matched over here. And for doing that, I am using this data fusion techniques over here. For doing that, I am using the AI and ML techniques over here. That's the idea. Now what happens in sometimes what happens, okay, so in sometimes what so sometimes what happens, my operating conditions change. So can I predict with different operating conditions also? So there is something called transfer learning. I will skip these things. There's something called transfer learning. In transfer learning, you can kind of predict with different operating conditions also. For example, this blue color over here and this red color over here, they are from different operating conditions. For this blue color, operating condition is different. For this red color, operating condition is different. But and therefore, if I'm not using this artificial intelligence technique, which is called transfer learning, if I don't use that, my prediction will be very bad. But if I use that, you can see over here, it is almost matching. Same way over here, you can see over it is almost matching. So there are AI and ML techniques which kind of help me to identify or to classify, to segregate, or to predict better. And that is the entire idea about artificial intelligence techniques. So my idea was that I will finish a little early, so that so now you have around 15 minutes to ask any questions and answer which you have over here. And this is basically all the conclusions which I am kind of listing over here. That what we have done, we have started with data processing, and then we did some kind of feature selection. And for feature selection also we used a machine learning technique which was random forest. And then we fused the technique. For fusing also we used dimensional prediction methods, and there were 14 different dimensional prediction methods which are also coming from AI and ML. And then we use this PELT, that is basically to identify which one is mild bearing defect, which one is medium bearing defect, which is severe bearing defect in a continuous data set. And that is also, that PELT also is a machine learning. And then we classified, and that classification is also machine learning. So we have done so many things over here which is related to machine learning, and that's all is being used for bearing health monitoring. So I will stop over here. I will leave the floor open for the questions, any questions that you may have.
If I will need the slide, I will use it again. Otherwise, kind of any questions you have, you can please ask.
Sir, my name is Professor. So I'm having a doubt in that kernel function, sir, in that supporter term machine. Sir,
Can you please a bit loudly?
sir, I'm having doubt in that supporter term machine
Okay.
related to kernel function. So in
Okay.
kernel function, it is converting that two dimension to three dimension or four dimension, and after
Right.
that, it is doing classification or regression like that.
Right.
So if you are converting to 2D to 3D, whether after converting to multi-dimensionally, we are applying that algorithm also.
You are again taking the projection. See. For example, there may this additional feature which you are kind of putting over here, that may be helpful for your classification. For example, you because you are doing this, you are kind of putting in higher dimension things which you are not able to see in a 2D. Okay, let me give a simple example. Means it may be a little bit abstract, but you, like for example, let's say now we are human beings, we are living in 3D. We have three dimensions, that is length, width and height. Now let's say there is a set of people who are living in 2D. So for those 2D people, they do not have any idea what is 3D. But for us, that is only a projection in a plane. That's what we are doing in engineering drawing. So when we are kind of putting in a higher plane, we can differentiate better. That's the idea over here. So that kernel over here is just to kind of differentiate better in a higher plane.
Okay, so my doubt no, sir. The model is built in the higher dimension, not in the lower dimension. If you are converting 2D to 3D, in the 3D only that classification, that supporter classification, that
Yeah, but eventually you're
hyperplane.
bringing it back. Eventually you're bringing it back to same whatever
Yes,
you
sir.
started with.
Okay, so that is what I'm having, sir. Doubt, sir. It will bring back to the original thing, and then it will give output.
Yes.
Okay, sir.
See, you
Thank you.
classify in higher dimension, but you bring it back and you say these are the clusters.
Okay, sir. Okay. For example, if it is line, we are making to hyperbola, and then again it will bring to line content, and
Not
it will give the
hyperbola, let's say something. Okay, let's say okay,
parabola.
okay.
First, for
Fine,
parabola.
hyperbola is also 2D. Let's say
Okay, sir.
okay, fine.
Okay, so again it will bring back and will give the results. That is okay, sir.
Right.
Okay, sir. Thank you, sir. Thank you, sir.
Hello, sir.
Yeah.
Somewhere you have used this fitness value.
Yes.
So what is the means simple definition of fitness value?
See how do we now what where I have used, that is basically I have used that fitness value where I had that 14 parameters. Like I had 14 techniques that were basically PCA and all those 14 techniques I wanted to compare, and there I have used that fitness value. So what has happened now, what initially I had that 72 features which I reduced to 15 features, and that I want to kind of combine those features into one single feature. But that which, like whether I combine by PCA or whether I combine by ICA or whether I combine by FA, factor analysis, which one is better? To compare between these techniques, what I have done, I have kind of found the different parameters which will be helpful in prediction. For example, if a parameter is continuously like this, it is easy for me to fit a curve. If a parameter is something like this, like this, like this, it is very difficult for me to fit a curve, because I don't know at one point what value I should take, because it is continuously varying, and therefore monotonicity can be one of the parameters. Same way, if a parameter has higher signal value and less noise value, it will be easy for me. Basically, I take those parameters which will help me in prediction, and I kind of join them and make a health factor or make a factor which will be useful for me for prediction. So that's what I have done over here. I have taken four different parameters which are monotonicity, prognosability, trendability and signal to noise ratio, and that I have combined together in a health index, and I have compared that health index for 14 methods, and I have chosen the best method. See, for those of you who are more interested in this, like all this whatever I am discussing, they are already published work. So I had a PhD student, his name is Sander Ambusia, and he has published this work in his thesis also, and so you can download these papers and all the details whatever I have presented in this presentation are mentioned in those papers. In detail, everything is mentioned.
That means we can take consider the average of these parameters, this testable.
Yes, you can take the average. See, if you are taking the average, then also you are putting that whatever I have initially said WM W. If you are taking the average, then you are putting everyone together. You are putting everyone same. So if you are taking average, everything is 0.25. So for taking average, what you are taking monotonicity plus prognosticity plus trendability plus noise you should divide by 4. So all those weighting factor, whatever I was saying, that is 0.25 for your case. But what I am saying that maybe monotonicity is more important than synchronicity. So maybe taking average is not good. Maybe I am giving much weightage to monotonicity and higher weightage to progressibility and maybe very little weightage to synchronous ratio. If I'm not taking average, that flexibility is there. But if you're taking the average, you're losing that flexibility.
Sir, good.
So related to
Yeah.
that feature extraction and where PCA and uses something 72 features.
Right.
So, how we are selecting these features gives a higher precision based on already we are measuring and classifying, and if the model is giving that classification, that feature is good, like that we are justifying, or
That's what
how
we are
we
doing in
are.
random forest. So there is something called brute force method. So what is brute force method is, so suppose I am doing bearing condition monitoring for the first time, or let's say I am working in bearing now. Now I move to gears. So now when I move to gears, I will not know which features are good for gears. So initially what I will do a literature survey and I will find all the features which are given there. I don't know whether they are good or whether they are bad. Initially I will consider all the features, whatever they are. And that's what I have done over here. I have initially taken 72 features. They are in different time domain, frequency domain, and time frequency domain. I have taken 72 features. Now, by using random forest, I am listing them in the order of preference, in the order of significance. So, what does random forest does? It kind of ranks the features. It ranks the features in the order of significance, and then I choose some top features which I feel are sufficient for me. That's the idea of it.
So I'm having doubt how the random forest is giving that ranking.
So random forest works on classification. So actually random forest, I didn't go in detail over there. It has multiple trees and each one of that kind of gives a decision and then it classifies which small subset. So basically what it does, it makes smaller subsets. So initially you have 72 features and it makes smaller subsets of 15 features, 12 features, 13 features and it will do that classification for all the subsets and to say there is the best classification over here. So suppose out of 72 features, I am going to get the best classification by using only 15 features, then it will say these are higher features. That's the idea. Now because these 15 features are overlapped everywhere. So like for example, if I take 15 features out of 72, I can select them in multiple ways, and some of the features can be overlapped,
Overlap in the
and
next
they are
tree.
yeah.
Overlap in the next tree. That is
No,
random
that's why I
forest.
get a ranking. Because it is overlapped, eventually I get a ranking of
Yes, sir.
individual features.
Majority would be based on.
Yeah, therefore I get a ranking of it. If there is no overlap, I will directly get the 15 features. But since they are getting overlap, I get a ranking that feature number 1, feature number 2, like that. Eventually.
Thank you.
And again see, for example, if you think over here, see if I simply take 72 features and I make a group of 15 features, I will get 72 to 15, which is a very large number. We cannot use for all that. So it is kind of some statistic is involved. Some kind of certain features are taken, certain features are not taken. That probabilisticness is inbuilt in
Okay.
this.
Okay. Thank you, sir.
Any clarifications?
So I have left out a lot. Means actually data acquisition itself, signal processing itself is a big subject. But here the topic was AI and ML, so I have focused only on those things which are somehow related with AI and ML. And so if any of you are more interested, they can go to my website, and I have listed all the publications which my group has published earlier, and many of those publications are involving AI and ML. You can download those publications and then they will have everything in between. Even after that, if you have some doubts and which you are not able to get cleared by going through publications or by this lecture which I have taken over here, you can write to me. I can type my email ID over here in this chat box over here. This is my official email ID. You can write to me and you can mention your doubt. I will try to answer in time. I will eventually answer to all your doubts. I will eventually answer to all your doubts.
Thank you, sir. Thank you, Dr. Piyush Shakya, sir, for your elaborate discussion on AI and ML for trading technology. I was discussing initially about the overview of the ML techniques and followed by Baring's concepts, covered the health monitoring techniques, and in that the classification, regression, segregation techniques were considered, and segregation diagnostics and prognostics approaches also has mentioned. And finally, prediction models, prediction consideration was discussed. In that LSTM technique was discussed. So with this, I think all the participants have benefited, and I hope they can now take interest in this area, the health management system on bearings. So thank you, Dr. Piyush Shakya, sir, for your valuable information. Thank you, sir.
I thank all the organizers for inviting me for this lecture. It is indeed exciting to talk about work and other things which I can do over here. Thank you very much for inviting me over.
Thank you, sir. Thank you.
Thanks a lot. So I will log off now.
Yeah, thank you, sir.
Yeah, thank you. Thank you.